Okay, welcome back after coffee. The third presentation of the morning is by Erik Schuenemann at Bosch. He's the manager for system engineering, powertrain subsystems, and powertrain solution in the Powertrain Solutions division at Robert Bosch. He has been there since 2015. He also worked at BMW Group in Munich from 1999 till then. He has a PhD degree from Friedrich Alexander Universität Erlangen-Nuremberg and is a graduate engineer from RWTH University Aachen. He's going to talk to us about hydrogen engine powertrains for future mobility. So over to you, Erik.
Thanks very much, Professor Turner, for the kind introduction, and thanks a lot for having the opportunity to talk to you, talk to this conference about our activities in Bosch on hydrogen engine powertrains for future mobility. Hydrogen engines actually are technology-wise are not so new, but they are getting a lot of momentum recently. I will start my presentation with some considerations on CO2 neutral mobility and some air quality considerations, a hot topic here in the EU. I will make the case for H2 engines, which show an exemplary engine system setup, which actually looks pretty familiar to current engines. I will show you what are we doing at Bosch regarding development of solutions for H2 engine powertrains. We'll show some results and wrap it up with a summary. We at Bosch are certain that we need to utilize all pathways towards CO2 neutral mobility. Of course, there will be electrification that starts with mild hybrids, full hybrid, then you can plug in the car, so plug-in hybrids. We have the battery electric vehicle, and of course we have the fuel cell. Of course, it's not sufficient to only look at this topic from a tank to wheel perspective. Yeah, we need to include a well to wheel perspective, even a life cycle approach. And need to make sure that electricity and hydrogen, of course, are produced CO2 neutral, which is not the case in many regions of the world today. However, also engine technology has clear pathways towards CO2 neutrality. There's a lot of activity in improving the efficiency of combustion engines. We have the large field of drop-in renewable fuels, which are a very interesting option because they are compatible with the existing distribution infrastructure, and actually these fuels are the only option to reduce CO2 emissions of the existing vehicle fleet of more than 1.2 billion vehicles worldwide. So very important topic, drop-in renewable fuels. Of course, the first e-fuel is actually hydrogen. And then maybe it's interesting also to use hydrogen in a combustion engine. So we think that following a technology open approach, when it comes to hydrogen as a fuel, both the fuel cell and the H2 engine should be included as possible solutions for hydrogen-driven mobility. Now we take a look at air quality, development of air quality in EU cities, in urban traffic hotspots. Most important pollutant components from our point of view are NOx and PN. Air quality wise, they are looked at as NO2 and particulate matter 2.5, so smaller particulate mass. And when we are looking at the potential that is realized and is brought on the road by modern diesel and gasoline powertrains like Euro 6D ready powertrains that are step by step introduced into the EU vehicle fleet, and we measure the pollutant emissions of these modern vehicles in urban traffic hotspots, like we have one here in Germany in Stuttgart, we realize that the emission situation, so tailpipe emissions, are very, very low, significantly below the current limits. And when we then use these tailpipe emissions in order to calculate the contribution to the air quality situation at this local traffic hotspot in Stuttgart, which is shown on the right-hand side of the picture, we see the diagram of NO2 air quality, where the limit at the moment in the EU is 40 micrograms per cubic meter. And we see the situation as it improves from 2015 to 2020 already. Of course, there might be an impact of the COVID situation here. But anyway, when we calculate the contribution of a modern fleet, which contains 100% of Euro 6D powertrains, so passenger car diesel, passenger car gasoline, and commercial vehicle diesel, we realize that each of the three powertrains contributes about 1 microgram per cubic meter to the NO2 air quality situation at the local traffic hotspot. And the non-traffic background contributes already 18 microgram per cubic meter. So it's clear that modern diesel and gasoline powertrains have a negligible impact on urban air quality already regarding NO2. And on the next slide, we see the situation for particulate matter, where on the left-hand side, you see a picture of 2013. So road transport, the red part of the cake, is about 20% of PM 2.5 emission situation in the EU. And road transport is basically containing of 4 components. One is PM that is coming from the exhaust gas. The second contributor is road abrasion. Third contributor, brake wear. And the fourth contributor is tire wear. And now on the right-hand side, we look at situation in the UK, which I think is pretty representative also for the EU as a whole. We see that the via introduction of modern emission technology, for instance, the particulate filter, the exhaust share or the contribution of exhaust to PM 2.5 is massively reducing at the moment. And that is even before any introduction of battery electric vehicles into the EU fleet or into the UK fleet. So massive reduction. And in the future, in the near future, it is already projected that exhaust emission contribution to PM 2.5 of road transport is actually the smallest contributor of all 4. So also regarding particulates, we can state that with modern technology, current gasoline and diesel vehicle fleet will have a negligible contribution to PM 2.5 emission. Now let's look at the case for hydrogen engines. Scientists at the Karlsruhe Institute of Technology in Germany have looked at the technology with a multi-criteria assessment. And up to now, some questions are open, but up to now, no exclusion criterion for H2 engines has been found. They contribute to very effective and pretty highly efficient fulfillment of energy goals and of course CO2 reduction goals. They increase the resilience and the robustness of the transport system by simply relying on another energy carrier. That makes us, let's say, makes the society more robust and more resilient compared to a situation where we only rely on one energy carrier. We see that in Germany at the moment, what the situation can be. Also, when we look at the contribution of the technology to welfare, for instance, social cohesion, we can see that basically this technology is interesting because it does not rely on let's say scarce raw materials that are let's say available maybe only in some parts of the world. The value chain is very nicely established already from the small supplier to the large OEM, even to after sales. So the job opportunities of these technologies are pretty interesting. So very interesting technology from this multi-criteria technology assessment, no exclusion at the moment. And that is also what we are seeing from our customers, so from our OEMs. The interest in hydrogen engine technology is massively increasing over the last years. And at the moment, Bosch is currently in discussion, planning or running H2 engine projects with more than 130 worldwide OEMs in all segments of mobility. That starts, of course, with heavy duty and agricultural machinery, because these powertrains have limited options, limited other technology options to achieve CO2 neutrality. And also, mostly they do not require a fully developed H2 refueling station network, because the large heavy-duty long-haul trucks are running at basically at fixed are using a fixed road network and are using basically always the same tracks. So basically, by strategically positioning the H2 refueling station networks, you can already achieve a full capability. So that's very interesting, and that's happening currently in the EU. You might know that I think last week the EU Parliament has pushed for more H2 refueling stations along the European road transport network. The goal is until 2028 to have every 100 kilometer along the European road transport network an H2 refueling station. I think that's very challenging, but anyway, the goal from their point of view is set, and hopefully the EU will follow. We also see significant activity in the light-duty vehicle segment, because H2 engines, powertrains could be of interest here for not only for light commercial vehicle like vans or parcel delivery services, but also for passenger cars. Actually, we think that it might start with rather larger passenger cars that are more suitable also for packaging of the tank system, and also are, let's say, more of interest for the customer for long haul transport. Interestingly, H2 engines are also a nice opportunity for high performance cars. So sports car applications or high performance cars are these OEMs are also looking more and more into that technology, because an H2 engine basically can keep the emotions in the game, so to say. That's why hydrogen engines are also of interest for these share of the powertrain segment. And we have a lot of other non-road and also stationary applications here. That's the good thing actually about hydrogen engines. Basically, there's a fit for every segment for these kind of technology. And how does it look like, the hydrogen engine? That mainly is determined by the properties of the hydrogen fuel. When we look at the, of course, you would like to have a high mixture calorific value in order to get more power or most power out of the engine, and that points to a direct injection engine that is turbocharged or at least boosted as compared to a natural aspirated engine. Also, interestingly, the auto ignition temperature of hydrogen is very, very high. And this clearly points to a spark ignition engine, so spark ignited, not compression ignition. Ignition limit lambda range is, let's say, massive. Yeah, so you can ignite a hydrogen air mixture that is very rich, but you can also ignite a mixture that is very, very lean. And the good thing, it can be homogeneous lean engine operation. It's not required to do some stratification, which of course, as a homogeneous combustion, has advantages regarding NOx formation, but also of course contributes to high efficiency. However, we might also see lambda 1 operation in some cases. This is especially interesting for high performance engine powertrains, where you maybe have issues to run these engines very lean because you do not get the air supply by the boosting system. And that points to lambda 1 operation, especially at high load. However, here you would need a combustion moderator, for instance, water injection. Now let's look at the, let's say, mainstream system layout of a hydrogen engine. On the upper right hand side, air is introduced into the system, flows via the air filter through the compressor of the turbocharger, charge air cooler. Then we have the throttle flap, and then the intake air is introduced into the cylinder. The fuel path is starting with a preferably 700 bar gaseous high pressure tank. You then have a pressure reducer to a pressure of roughly 20 to 50 bar. That is then routed to the pressure regulator, which is positioned close to the engine. From there, we go to the fuel rail, and from the fuel rail, the fuel is distributed either towards the PFI injectors or towards H2DI injectors. Then we have the ignition, where ignition system has a little modification, coil, spark plug. Some modification. Spark plug needs to be very cold to avoid irregular combustion from the hot surface of the spark plug, but that is doable. Then you have the combustion, and the exhaust gas is then routed to the turbine and spools up, drives up the turbocharger, and then it goes to the emission after treatment, exhaust after treatment system. Optionally, you could have a cooled external EGR. And when we look at the after treatment system, that consists mainly of three components. One, oxidation catalyst. Number two, particulate filter, which is for the engine oil combustion and particulates that are generated by the engine oil, because we want to be clean over lifetime. And then we have an AdBlue SCR system for DeNOx. So looking at the components that need to be addressed. So as I mentioned, particulate filter for particulates coming from the engine oil. Values are extremely low, but we want to make sure that these are low over lifetime. So especially for heavy duty commercial vehicle commercial vehicles, we have significant lifetime, so 1.5 million kilometers. And it might be the case that engine oil consumption is increasing over lifetime. And just to make sure that that we are on the safe side, we recommend to introduce particulate filter. HCCO only coming from the engine oil, because there is almost no C in the hydrogen. And of course, the oxidation catalyst is, of course, in a lean burn after treatment, we have sufficient O2 So HCCO are converted. Also, the oxidation catalyst is converting any unburned H2. Also important, maybe also due to safety reasons. And then we have the AdBlue SCR system for the NOx, where we basically are targeting to carry over the proven AdBlue SCR system as a first choice. What is Bosch bringing to the table? A lot of our components are available from gasoline and diesel applications, or can be derived with small modifications. Of course, we need the H2 fuel system and especially the H2 DI injector. These are new developments here. Development is ongoing. Bosch is developing H2 engine control units and software solutions that include the actual engine control, the AdBlue dosing control, and the hydrogen storage control unit, and the respective software solutions as well. Of course, e-Powertrain functionalities for the hybrids. And Bosch is also developing, together with partners, gaseous H2 tank system solutions. So we are positioning ourselves, that's our goal, to be a system supplier. Regarding H2 fuel injection, there are several options on the table shown on this slide. From left to right, complexity and cost of the fuel injection system are increasing. Starting with port fuel injection, which is preferably a multi-point injection, which needs to be mainly open valve injection. That means we need to inject the fuel while the intake valves are open to minimize the risk of backfire. We consider this solution as a quick path for lower requirements and shorter time to market. So we expect these fuel injection system to be the first that comes to the market. Then next, on the right-hand side, we have a low pressure direct injection. That is what we see as the preferred path. Almost all light duty applications are following H2, low pressure H2 direct injection. We are developing an injector. First samples are running in the engine currently. And then on the right-hand side, we have high pressure DI injection. And high pressure DI injection together with a diesel pilot, which acts basically as a compression ignition, the diesel injection. Currently, we do not follow at Bosch these two options. When we have an H2 DI system, we would like to inject the fuel after the intake valves are closing. That gives us shorter mixture preparation time and shorter time for homogenization. But we want to have this kind of injection strategy because by this we would avoid interference of the H2 fuel injection with the intake air. Hence, we need to have as much as possible air inside the cylinder after the intake valves are closed. That's why we are targeting closed valve injection. So after intake valves are closed, and that gives us less time for homogenization. That's why we are targeting to support the homogenization process by guiding of the jet, which is normally, when we do nothing, we have basically a hollow cone jet, like we have it in typical gasoline outward opening injectors, for instance, for the stratified injection system or stratified combustion systems. So that is basically the hollow cone that is formed when we do nothing. This configuration has the risk of getting early contact in a center mount position, but also in a side mounted injector position, early contact with hot surfaces like the spark plug or maybe the exhaust valves. That's why we are considering as an option potentially to recess the injector tip a little bit, maybe in this case 2 millimeters from a flush mounted position. And then we have basically the injector bore guiding the jet downwards to the piston in a center mounted position. That is what we are seeing here. So that's an option that is pretty simple and, let's say, minimizes also the risks that might be associated with other options like jet guiding caps that are shown here. So we can completely modify the axis of the H2 jet by putting a jet guiding cap on the tip, which might also have risks because it can get hot and it has kind of a dead volume. So we are not so sure if that's a good solution for every application, but it's an option to guide the jet. Also, in cases where we do not have sufficient charge motion, we also can improve mixture by basically simulating a multi-hole injection, like we are doing here. So that increases the surface and from our point of view, increases mixture formation, mixture homogenization, especially when the base engine does not have a lot of charge motion like tumble motion. Now, when we look at the potential regarding engine out NOx reduction and exhaust temperature, in this case for a heavy duty application, as compared to a modern state-of-the-art heavy-duty diesel engine, looking at engine out NOx, left-hand side of the picture, we are seeing that by going to hydrogen, we can reduce engine out NOx by more than a factor of 6. And also a very nice result is that as compared to the diesel engine, we have very nice exhaust gas temperatures before the EGT system, that is the AdBlue SCR reaction is demanding. So very nice benefits for the hydrogen engine that leads to even lower tailpipe emissions and relieves a little bit the requirements on the exhaust after treatment system. When we look at efficiency and compare the hydrogen engine to the fuel cell, we must say that for high power applications like agricultural machinery or heavy duty truck engines, the efficiency of the fuel cell powertrain as compared to the H2 engine powertrain is already on par. Of course, in passenger car applications where the engine is a lot of the time running in part load, the fuel cell has a significant benefit regarding efficiency. But I think we can shrink the gap. Actually, we can use the same approach like we do it with gasoline engines, and that this is hybridization, which basically means shift the engine operating point to higher power. And that means improve the efficiency of the engine as compared to the fuel cell. And that was done here in a work that we did together with Professor Eichelseder, who also presented already on the conference from TU Graz. As compared, we compared two powertrains and two engines, basically a baseline H2 engine, turbocharged DI engine, 2-liter displacement, and compared it to a potential dedicated hybrid engines. You see that the high load area is cut off. We are providing the power with the electrical part of the system, and that gives us basically two options. One, we can avoid engine operation in the high load where we, let's say, we have some issues to provide sufficient air to the system. So skip the high load operation and reduce NOx. And the second option that we have used here is use the degree of freedom that we have in order to optimize efficiency like we do it for the dedicated gasoline hybrid engine already in the sweet spot. And when we are doing this and looking at the hydrogen consumption of these two powertrain options in a medium class sedan, WLTC H2 consumption, the conventional powertrain has around 1.6 a kilogram per 100 kilometers H2 consumption, and the serial parallel hybrid has around 1 kg per 100 kilometers. So we can reduce fuel consumption by this approach by roughly about 1/3. And when we look at engine out NOx, especially in a highly dynamic driving cycle like the RTS 95, that simulation shows us also what we have expected, that we can reduce engine out emissions significantly by avoiding running the engine under high load operation. So engine out NOx is significantly below future Euro 7 limits. And now we add the AdBlue SCR system with roughly 90% conversion efficiency over the complete cycle. And then we are arriving at maybe 1 to 2 milligrams NOx emission per kilometer. So we would, let's say, definitely consider this as zero impact. So that's a very nice option here. I would like to wrap it up. We need a technology open approach. That's more and more clear. And because only the technology open approach leads to the best future powertrain solution for each application. And here, of course, battery electric fuel cell and H2 engine are complementary. The introduction of latest emission technology into the vehicle fleet will already lead to negligible exhaust gas contribution to the air quality due to better initial conditions. That means engine out emissions. This also applies to H2 engines. We are seeing significantly increasing worldwide interest in H2 engines. We are working on components, subsystems, and software solutions to position ourselves as a system supplier for H2 engines. And we on Bosch side, we are convinced that H2 engine powertrains will become a very important part of future mobility solutions. Thank you very much for your attention.
Erik, that's a great presentation. Thank you. I think we've got time for a couple of questions, if there are any from the floor. Yes, one.
Hi, good morning. It's a nice presentation. I have a question regarding.
I think the microphone's not on. Yeah.
Okay. I have a question regarding the electric cars versus the hydrogen-based machines or the cars. Have you done economic analysis to show in terms of if you end up introducing a hydrogen-based car versus the electric cars in terms of over the life basically cycle of the car, which one would be more competitive, okay, for the end, for the customers? Thank you.
I think that's like all of these life cycle questions. If you talk about the topic with experts, they always say, "Oh, it depends," as always. We are working in Bosch on all the solutions that I presented in the first slide. So we think that in the end, the market and the customer will decide which solution is the appropriate for his task, for his application. And also we think that there will be regional specific differences in the solution. That will be mainly from our point of view defined by how the energy system of the region or of the specific market looks like. Yeah, so for instance, in France, where you have a lot of nuclear power, so CO2 neutral base load power, maybe the electric vehicle is a good solution for the mainstream. If you look at other markets where the electricity is far from being CO2 neutral, and where the general energy demand, the primary energy demand is much higher than what can be provided locally. For these markets, the energy system demands the import of energy carriers. And then the next question is, what kind of energy carriers will that be? It will definitely, from my point of view, chemically bound energy carriers. That means gaseous and or liquid H2 derivatives. So that's the situation on the, let's say, on the energy system, on the fuel system. If you look at the technologies or powertrain solutions, basically, to compare, like battery electric fuel cell or H2 engine, also it will be application dependent. Example, heavy duty truck, long haul truck application. The battery for these kind of, if you would like to have such kind of a vehicle, as a battery electric vehicle, battery weight is 10 tons. Charging of this system, very difficult. You need high charging power installations along the highways. That points to other solutions, where hydrogen might be an interesting option. So that's one example. For other, for small cars, where maybe the driving range requirement is not so high, and when the customer can charge the vehicle overnight, of course, battery electric is interesting. However, if you then go, let's say, to mega cities like maybe Shanghai or the Tokyo area, I would say there are not so many customers that can charge the vehicle overnight, even the small cars. And that points to a situation where you might need a different solution for this, right? And that points maybe more to hydrogen or engine solutions in general. Yeah, so it depends. But we clearly see that the hydrogen engine is a very attractive part of the solution here.
Okay, well, thank you very much. I think we're going to have to draw it to a close now, but thank you very much, Erik. Thank you.
Hey, thank you.